Good afternoon, everyone. Let me double check I am recording. Stop video. All right, looks like recording is happening. Okay, well, welcome back. It's November, if you didn't notice, which means we are already learning about NLP for 2 full months, and we have another month to go. Since I've been going so slowly, this month is going to be equally important. Usually at this point, of course, I'm like, oh, I had enough to say, and students probably had enough of me. But I feel like this time around, we still have to cover some important topics. Before I get into the main theme of today's lecture, I just want to mention one detail that I didn't get to talk to last time. And this is the idea of continued pre-training. I have told you what kind of data we use for pre-training. And you know, there's lots of data and it comes from diverse sources, but it's not going to happen when hired by a company that has very specialized data. And most likely that's going to be the case. That's why they have a business model, because they have some special data that no one else has and it's not readily available on the internet. Think about financial data. In this situation, it can be helpful to take whatever pre-trained language model is the best pre-trained language model right now, and you have its weights, and use that data you have and continue pre-training on the data you have. So basically, you take your pre-trained model and you do what you would do if you were pre-training from scratch. You just have these fancier weights that you usually use for fine-tuning, but you can continue pre-training with other sources of data. And that can make your model that already knows a lot about the language even more specialized for your domain and better for all kinds of applications you are interested in that domain. So think about financial or medical data. This is where this extra trick will help you. Here I am presenting results from our paper where we said, like, despite this huge pre-training data and this being general purpose models, if you are still adapting to your domain, you can have improvements. So these are without this domain adaptation, and these are results with the adaptation. And if you compare these columns, you will see that there are benefits of adapting despite pre-training data already being quite diverse. So just remember that trick if you are, in a situation where you work with more specialized data. Okay, so so far we have covered pre-training, and this is not enough to know what large language models are. There are two other major components. One of them is instruction fine-tuning, meaning we will use some supervised data, meaning data where outputs are now actually written by human annotators. And these days in 2025, we are going to use some synthetic data here as well, meaning data generated by the best available model. With some caveats of, for example, OpenAI's terms and conditions say you can't use their outputs to train your model, and whether that's violated or not is something we are going to briefly talk about. And then very importantly, and the reason why we had ChatGPT in the late 2022 was because of this final stage of alignment, meaning aligning your model's outputs with human values, which means typically that we do not want models to produce text that's obviously hateful or that is aiding in unlawful activities. Previous to that, all chatbots would go rogue in a matter of a couple of hours, and we didn't have helpful products like ChatGPT. So that was another important stage. So now, instead of talking about how to do these stages, which we will come to in a couple of weeks, I decided we are going to talk a little bit more about applications that we can tackle with the technology we have learned about so far, which is we take a pre-trained language model and we fine-tune it with the data we have at our disposal. I felt like it's going to refresh us a little bit to go away from this more machine learning topics and into more NLP-ish topics. So this is just a decision I made, but we are definitely going to come back to learning what instruction fine-tuning is and what RLHF is. And with all of that, we are going to more or less come to what large language models are. There is still an active area of development here. So these days you might have heard about reasoning language models, which are basically large language models that are designed to have really good reasoning capabilities. What is reasoning is very overloaded question. But these days we deem that reasoning is something along the lines of answering questions that require multiple steps of intermediate processing, and the model is going to verbalize these intermediate steps like its own thoughts. And by doing this, we will solve very challenging problems in programming and mathematics, for example, where reasoning is really important. We won't go into any depth of what reasoning language models are. By the end of the course, I might mention what are the key ingredients here. I don't know what was the sound. Hopefully everything is okay. Okay, but as I said, we are going to now go into applications, and we are going to embrace this paradigm of we have some pre-trained language model that has been pre-trained with language modeling objective, for example, on lots of data, and using the weights of that model and some label data we are going to fine-tune it for application we have in mind. And we are going to start with question answering, which is actually a suite of a bunch of tasks in NLP. So the first thing I'm going to cover is various flavors of question answering we have in NLP. This won't be the most exciting part of this lecture. It's going to be mostly going over a bunch of terms we are using, but it's important because later on, when you need to make development decisions, you are going to choose which flavor of question answering you are going to choose for yourself. So it's important to know some of these terms, but as I said, it's not going to be the most excited part of the lecture. And then we are going to dive into how to tackle open-ended, open domain question answering, meaning if I give you my system question about anything, and I don't give it any kind of source text where the answer could be, how can it find relevant documents, and from those documents identify and then provide me with the right answer. So we are going to talk about architectures for that and then go deeper and deeper and deeper. Okay, before we dive into this, are there any questions? Yes, please.
The final exam is scheduled on the December 13th or December 12th in person. The scheduled time is 1 to 3 p.m. Is that correct?
The exact information is on the webpage. Yeah, so check the webpage. Yeah. Okay. Okay, so let's start with question answering. So all of us, we are filling our information needs by talking to virtual assistants or searching information, or now turning to chatbots. So given this obvious need in the real life, it's not really surprising that question answering has appeared as a major task in NLP, similar to machine translation, right? This is a really obvious need by all of us in the world. So obviously, that's going to become a huge thing in the natural language processing, which the whole goal is to create solutions to applications to fulfill such needs. So now, there isn't one question answering task. And the first dimension along which I want you to think about question answering is in NLP is what is the intent behind the question? Intent behind the question can be you have some information you need and you want to find that piece of information, right? So this is pretty straightforward and something we are all accustomed to because we do this all the time in our real life. However, there is also another intent in natural language processing behind questions, and that's to test whether a machine or some other person knows the answer. We want to probe the ability of this person or a machine. The task of question answering, when I say question answering in NLP, it's usually referring to this first intent behind the question, when we need to fulfill some information need. So the questions are typically real queries by products that that we can give to products like Google Search or Reddit or Stack Overflow. questions are therefore very ill-specified. I don't know how you write your search queries, but mine are absolute disaster with misspellings and very underspecified and so on. So there is a lot of ambiguity in what we say presupposition. They are less frequently involving complex reasoning. This is now maybe changing with chatbots, right? But think about search engines before ChatGPT. Your queries weren't necessarily these very involved, complicated queries. Rather, they were something more straightforward, and you kind of change your language such that you can get the best result, right? Questions often assume that you won't give any special context and that we almost never pose our questions to search engines as multiple choice questions. And you would see in the NLP research that these kinds of works are often funded by industry because this is where the real needs come. So for example, this is one question answering task. It comes from the dataset called Natural Questions developed in Google. Here, the question is, when are hops added to the brewing process, right? So it's very open and open domain, right? I can ask completely other questions, a natural question, and will have nothing to do with brewing, and it can be about something completely different. And the idea here is that the model will find a relevant document somewhere on the internet, for example, from Wikipedia. And in this document, there will be a relevant piece of text that's going to serve as the answer, such as the boiling process. Or if we want to have a little bit longer answer, we could give the whole paragraph where the shorter answer occurs in. So this is an example of a question answering task in NLP. Now, I mentioned there is this other intent where you're trying to probe the knowledge of the machine. And this is what we are going to typically refer to reading comprehension tasks. Here, the task is you are providing a piece of text to your system. You are not testing its retrieval capabilities. You are not testing whether it can find the answer on the internet. You are actually interested whether it can reason over the text such that it can come to the answer through its ability of reasoning. So here you will always give a piece of text. It can be a document or a passage. And you are going to probe the answering capability. So this is an example of such a task coming from the dropped dataset. Here the system, the model receives a passage. You are giving it to it. You are not expecting the model to retrieve it. And given this passage and this question, how many touchdowns were scored in the second half, the model needs to provide an answer, and the correct answer here would be 2. Now, I invite you to kind of skim over this piece of text. The kind of impression you should get, you see plenty of numbers. So there is some kind of reasoning over numbers and quantities, and the model needs to do some inference to come to this answer. Similarly, here we have another reading comprehension data set of tasks where we are probing models' understanding of implications of negation. So the question here was Parsons able to use his Jaguar car after the fire? The relevant piece of text is that nearly all of his possessions were destroyed, with the exception of a guitar and his Jaguar automobile, meaning that since car did not, it was not destroyed in the fire, it could have been used later on, and the right answer to provide here is yes. So we are testing the model's ability to handle negation. Okay, so I hope it's clear this distinction between trying to build a system that can answer questions such that people can receive information, and building reading comprehension data sets to test models' reasoning skills. These are completely two different goals, but they are all seemingly looking like question answering tasks, right? Okay, now, I also want to emphasize that almost any NLP task can be formulated as question answering, and I want you to understand what is truly question answering as a task and what is question answering as a format. So let me see here. So I will just skip over all of this. For example, we have worked with sentiment classification, and we could easily frame our sentiment classification into question answering format. We could have given our movie review, and then after every movie review, we could add, is this movie review negative or positive, right? Is this now question answering task? I want you to know it's not. It's the question answering format, but let's go into that a little bit more. So when a question answering is to determine whether your question answering instance is really a task instance of question answering or just a question answering format, you can ask yourself, how hard would it be to replace the question with some, what I would say, content-free identifier, meaning something that that it's not rich in content. And to make this a little bit more clear, look at this problem of, I think there is a typo here. What is the sentiment of this statement? You could have easily replaced this with statement, sentiment column, right? So this question, what is the sentiment of? You could replace it with sentiment column. And in that sense, that's content-free because it's always the same regardless of the movie review, right? Maybe to drop this word content read because it sounds very jargony and technical, just think about how easy it would be to replace the question with some tag, right? Like sentiment here. And in this case, it would be really easy. And for every question, we would just use sentiment column. However, there are also data sets which are, we say, template-based. You have very predefined set of questions you would ask. So at some point, there was a task where given Wikipedia pages of famous people, you could ask, when was this person born? Where were they born? And it was always a fixed set of questions you would ask. And here, although the questions are a little bit more diverse than just what is the sentiment, you could still replace them with something like born column, right? Or time born, or something like that, year born column, and so on. So again, you are in a position where, although questions are changing from instance to instance, they are changing in very restricted ways. So I can again define some special tags. However, when the task of question answer is really open-ended, such as natural questions, where one of the examples was, what is the next stage of the brewing process or whatever, or when are the hops added to the brewing process, this is where the question has rich semantics and you couldn't just replace it with some special tag, because the next question will be completely different than that question. So if this is maybe a little bit hard to follow, just in the natural questions data slide, I left you a link where you can see different questions, and then try to think about, okay, if I would use some tag or something to replace all of these questions, or like few tags to replace them, you would quickly notice it would be really hard. Okay, so remember here, anything can become question answering, but a real question and answering task, the question itself, it needs to matter, right? Here, it doesn't matter because I can replace it with sentiment column. Okay. Questions about this? Yeah.
So could we think of things that are more question answering formats as essentially being like lookup tasks versus something where the question is what matters? If you can't look up the question.
Oh, I think for me, lookup invokes this idea that your answer options are, you need to just take something and that's it. With classification, you still need to determine what is the class for a given input. So I think what you're saying kind of suggests that we could call classification as a lookup, where that doesn't sound right to me because I just know it's a little bit hard to explain, but it's not like we lookup kind of suggests to me that for every movie review we have its class somewhere available and we just need to look up what it is, right? In that sense, I don't think that's the right word to use here, but I feel like you have a right sense of what's going on here. We are maybe just disagreeing on whether lookup, the word, can be used here.
Right.
Okay, and Later on, when we introduce instruction fine-tuning and we talk about prompting, this is where the question answering format becomes useful because it can be used to prompt models for various things. So we are going to come back to it. Okay, continuing with different kinds of question answering tasks. Now we are going to zoom into what kind of questions can exist in the data set, and then we're going to look into what kind of answer formats we're going to have. And this will kind of map various data sets we have at the disposal. Again, not the most exciting part of this lecture or this class, but it's important that we are familiar with these terms. So for questions here, you have four formats. The most normal way to think about question is it's a question, right? Natural language questions. So here we have when was Einstein born? That's just a natural question, the way that a human speaker could ask. We can have, VH questions and also yes, no kinds of questions. However, very often, for example, where we use search engines, we are framing our questions more like queries. So here, which year Einstein born? That's not really a natural language. We don't speak to each other like this, hopefully. But it is inferred that this is a question seeking information. Now, the next two are less relevant today. There was a point in time in NLP research when we were developing data sets that are of this format. You wouldn't find them often today. So one of them is this close format. Such an example of it is Einstein was born in blank, and then the model had to fill in the blank. Any ideas why this would be a popular choice for question answering data set in, let's say, 2018 or 2019? Yeah.
Makes sense with how our encoder model works.
Exactly, right. We were pre-training our encoder model with masked language modeling objective. So if I had framed my queries like this, then maybe my model would have better capabilities to handle these kind of queries rather than natural language ones, especially if the answer was expected to be generated. Another one which you will see very, very rarely is story completion, where here we have a beginning, incomplete part. Einstein was born, and then we give two options to a model, and it needs to choose one of them, which would better complete the given piece of text. This was used at the time when we were also trying to test the reasoning capabilities of the models. So by maybe needing to use some common sense reasoning to choose which ending would be more plausible, we can see whether the model had that capability. Again, not something you would see very often today. Today, we would mostly see natural questions because we made so much progress that we can actually handle just natural language questions, and they are the most natural ones. Okay, now moving on to answer formats. Again, you will have four different answer formats. The first one will be so-called extractive answer format. So imagine either I have given or the model had retrieved a relevant piece of text, such as here, Einstein was born in 1879. The extractive answer here would be to find the span of the input text, which answers the question. So let me just open all of these. So here we are going to go in details of how to go about this, but basically imagine every token has its position, which of course it has 0, 1, 2, 3, blah, blah, blah. And we need to predict the starting and ending position of our answer span. So imagine here the tokens are actual words. We have Einstein is 0, was 1, born is 2, in is 3, 1879 is 4. The model should have predicted as a starting position 4, as an ending position 5. I mean, depends how you implement it. You can say ending position is also 4, but it's going to be easier if it's 5, and then you take what's in between. Okay, so with extracting answers from the input text, what is nice here is that there are finite number of possible spans in a given input text. So your evaluation becomes a bit easier than if the model is generating the answer, where the number of possibilities is infinite. If we don't approach extracting the answer by predicting the starting and ending positions in our input text, and rather generating the answer, this becomes a case of retrieval augmented generation of RAG that you might have heard about because it's pretty hype these days. And we are going to go into details of retrieval augmented generation as well. Okay, what else I wanted to hear? See, oh yeah, one limitation with the extractive question answering is that answer is limited. Sorry, the questions you can ask are limited to what can be answered with a given piece of text, right? If the answer must be a span within a piece of text, then you can't really ask whatever you want, right? If you want to ask something that has to be answered with a given piece of text and some extra knowledge, then that's no longer a possibility for including that kind of a question into your extractive question answering dataset. Okay, then we have multiple choice format where, given a question, you give A, B, C, D, like your midterm exam is an example of multiple choice format. And here the benefit you get is that now you can ask questions that require reasoning about the input piece of text, but also something extra, right? For example, I don't know if you require some extra knowledge coming from some knowledge base. The problem is that writing really good negative questions, negative options is really hard. And this is why I can't, when you ask me, we have practice exams? I'm like, no possible way I can imagine more of these. It's really, really hard to come up with the negative answer options that aren't trivial for the model. So that's something to keep in mind, and models have been found to kind of cheat at these multiple choice formats. For example, models, when they don't know what to do, they just pick the first option, and we call this position bias. Now, if you have developed your benchmark in a way where the first option is often the right option, the model's performance will be inflated and will look better than it is just because it has this position bias and it's going into its favor. Okay, then categorical format, honestly, not so important. Here, some people will call it categorical format. To me, this is very like multiple choice. The idea is that the answers come from predefined set of answers. In the most common case is when answers can be just yes or no. To me, that's very like multiple choice format because then the options are yes or no. And finally, the most interesting one is the free form format, where answer can be whatever, right? It can be a piece of text. It doesn't have to come from the given input text. It can come from anywhere. This is nice because you can test models in their ability to generate longer text, right? Where the answer simply requires something more than a short snippet of text. For example, in medical domain, you will find a lot of such answers where you simply can't just give a short phrase to answer the question, rather there is some explanation, justification to answer the question. And of course, the most challenging part about having free-form answers is the evaluation, right? If I can generate whatever, how do I know whether that's a good answer? Like a little rephrasing of the true answer gives me another piece of text that looks very different. I can use all the different words. And although lexically these two answers aren't different, they can easily say the exact same information, right? So once we've done the question answering, we are going to turn to summarization, and we are going to talk at length how to evaluate text generation. We are going to talk about automatic methods and using human annotators to evaluate the quality of generated text. So that becomes relevant here, but we won't talk about it yet. Okay, so these are basically all the kind of dimensions of question answering I want to mention. Remember that I started with what is the intent behind the answer. Behind the question, is it to get the information or is it to probe the model's ability to reason over the piece of text? And then we have looked into 4 different question formats and 4 different answer formats. And we have also talked about how anything in NLP can be question answering alike, but what matters is that the question itself has a rich semantics and you can't replace it with some placeholders. And that's the true question answering task rather than the format. Okay, now with all of that, I want to go into how to, develop models to do open domain questions. Are there any questions before we go further? Okay, yeah, as I said, it's not the most exciting topic, but it is important to know all these terms. So now let's get into more exciting stuff. First of all, open domain question answering is referring to the task of asking a model to produce answers to typically factoid questions in natural question. And the open domain part is referring to the fact that we can ask all sorts of questions and the relevant content is not given in the input. Rather, the model needs to find the relevant input. If we have given a passage or a document, that would be a reading comprehension task, right? Remember also reading comprehension versus just open domain question answering. And you won't provide answer choices in your input. So it won't be the type of multiple choice question answering. Now, general idea also here for having this retrieval component is that large language models data, pre-trained data, potentially did not cover relevant information. So the model can't just answer the question because it has never encountered the relevant piece of information, or it has encountered it so far, back that it's forgotten the relevant piece of information. So we need this relevant piece of information, and once we have the relevant document or a passage, then we can condition the answer generation or answer extraction based on that context. Here is a visualization. So today, when you use, it's really hard to say which kind of flavor of ChatGPT or Claude you are using these days. But maybe like in 2023, you certainly use this kind of approach where you just given a question to your LLM and it didn't use any kind of search over the web or retrieval of anything. Rather, it generated the answer based on what's in the parameters. And we call this ability, or how to say that, where the information comes from when you are generating the answer in this way without having any access to external memory. We call this parametric memory. Parametric because we have parameters of the model, and somewhere in these parameters of the model, information is encoded, and the model is using its parametric knowledge to answer the questions, right? It doesn't use external data store or external memory. So you will hear this parametric versus non-parametric knowledge distinction. I'll write it here. So parametric. This is the knowledge that is somehow encoded in the weights of your transformer-based language model. And you would need more advanced interpretability techniques to understand how exactly is encoded and where is encoded and so on. Non-parametric refers to these external databases, right? Think about file system on your computer. That's non-parametric knowledge, something that you can actually physically open a file, right? Okay, now here we have 2 instances of so-called retriever-reader or retriever-generator architecture. Retriever refers to the component of the architecture we're giving your question and giving some data store of hundreds of millions of potential passages or documents. You are retrieving those that are most relevant to your query. And given those, you place them into input of your large language model. And then based on those relevant documents and your same query, you are prompting the model to give you the answer. This architecture and this architecture differ in so-called reader part. That's the part that gives us the answer. Here, we have a reader that's going to predict which tokens in the input, which positions are the starting and ending position of our answer, right? So if I had some piece of text, like we had previously, as I said here, Einstein was born in 1879. If answer 1879 is starting at this position 4, at that token, the model should predict you are the starting and ending token. On the other hand, the retriever generator architecture is going to also take the relevant document, so the input doesn't change. What is changing is how the answer is provided. Instead of trying to find the starting and ending position in the input text, the generator is going to generate with next token prediction what is the answer. So the answer might be exact same, string, such as 1879 in the previous example, but the mechanism we use to obtain this answer will be different between retriever reader and retriever generator. And we are going to go into details of how to retrieve. Then we are going to go into details of how to do this reader extraction providing of the answer. Then we are going to see with the generator, you already know. You already know how to generate with the next token prediction. So that you're, okay, I know this part. But we're going to talk about how to combine these two components in retrieval augmented generation, in this retriever generator, for our training. We can train them separately, we can train them jointly, we can train them jointly in different ways, and so on. So I'm going to talk more about that likely next time. Okay. Are we kind of having a sense what we are going to talk about? Like, of course, you don't understand all the details because I didn't give you them. But generally, we are all on the same page where we are heading. Yeah, okay. Okay, let's then jump into retrieval. Retrieval will be necessary for both retriever reader and retriever generator. So retrieval is going to, given our query and given some data store with relevant documents, is going to give us rank documents and give us top, let's say 3 or however many we are interested in. And for that, I'm going to start with some more classical approaches, and then we are going to talk a little bit more about more advanced approaches. So we all know what TF-IDF is. Remember, it's been 2 months ago for sure, but when we started to talk about NLP, we have started to talk about these very basic ways of representing input text. Now we have come a long way from there, but we are coming back to the TF-IDF. And TF-IDF, basically for every possible token in my vocabulary and every document I have, it calculates the TF-IDF value of that token for that document, which was the product of its TF value. So how many times that token had occurred in that particular document, multiplied with its inverse document frequency, which is inverse of in how many documents this term had appeared in. So basically penalizing terms that appear in too many documents because they are not the discriminative tokens that are special, right? If I have a token that appears only in one document, it's really special. It appears just in this document, so it has more importance. So what we can do, or what we are going to do, we can calculate this score. And score for a given query relative to some document is going to be the sum of all TF-IDF value for tokens appearing in that query relative to that document. right? So very, very simple way of calculating the score between a query and a document. And one famous algorithm for doing classical information retrieval called BM25 is basically a more refined version of TF-IDF. It's basically going to have two additional hyperparameters called, of them is called a knob, and the other one, I don't think it has a name, but it's going to control the importance of document normalization. So basically what you're seeing here, focus for a moment on this line where I have score for a query and in a given relative to a given document. So we have the sum of TF-IDF values, right? And TF-IDF value is a product of TF times IDF. So basically, if you ignore this denominator, you have the same thing written, right? The sum of IDF times TF, although here we have that log. If you remember, I mentioned, all right, maybe you want to, if a certain document appears in 100 more documents than some other, we don't want its IDF value to be so much different. So by using logarithm, we kind of tone this down. So here with BM25, we are basically having this fancier denominator here, which is doing two things. One is this hyperparameter B is going to basically control that the documents that are longer, so they have a higher chance that more tokens in a query appear in them, don't artificially get higher in importance. So that's the purpose of this part over here. And K, the knob, is going to basically give us opportunity to say how much, basically lower the importance of the TF, term frequency, in the TF-IDF. So lower this K is, and if it's really, really low, then basically what you're getting is high effect from IDF. And this really depends on the application you have at mind. For example, if you have very short tweets and you want to see whether some new keyword had appeared in it, for example, earthquake, maybe having our earthquake being mentioned, which can be kind of measured with IDF, is more important than TF of that term. Or if you have a very special term in scientific literature, maybe the fact that it is going to appear in less documents, so you want to emphasize IDF. In any case, what is important for you to remember that BM25 is a version of TF-IDF, and that through using TF-IDF, and it's this fancier version, I can get a score of a query for a given document. And in this way, I can rank all the documents and return the most top 3 ones for the retrieval. Okay, is that clear? Yeah.
So these retrieval algorithms that we're talking about right now, they're not actually like neural models that we've been focusing on before. They're just mathematical algorithms.
Yeah. So here, it should be self-evident, right? Like here, we are just using the term frequency and inverse term frequency, right? So it's just statistics of the data. We're not using any neural stuff here. Yeah.
Okay.
Okay, I'm going to go further, but reason why I'm starting with classical information retrieval approaches is because BM25 is still a very strong baseline. So anytime you are developing new retrieval system for new application or new data, you should always calculate BM25 as your baseline for whatever approach, including neural approaches we are going to learn in just a few slides. It's still very powerful. So we recently had developed a benchmark for assisting attorneys who write legal briefs for Supreme Court. These are documents where attorneys provide their basically maximal position to kind of convince the judge that this is a position they should consider. And then the judge does all the extra stuff and makes actual decisions which are more neutral. And for this, we have proposed a task where, given prior case law, we wanted to an attorney to be able to say, okay, I want to make this statement. I want to find the most relevant case law for this statement. And we have seen that our fancier neural baseline underperformed this BM25, and this was released this year. So to this date, this is a very relevant baseline that you should always calculate. Okay, moving on, we need to talk about this inverted index. So basically here, you see that it's maybe for me clearer here that this sum is going to be 0 if none of the terms in my query appear in a given document, right? So for a given document that does not contain any of the terms in my query, the score will be 0, and I should ignore all such documents. So because many documents will actually be like that my query's tokens have nothing to do with it. It's really important for me because now I'm starting to work with the scale, right? Imagine Google search how many web pages the search engine works with. I need to quickly identify what are the documents I should simply ignore. What are the documents that do not contain any of the tokens in my query? And for that, we are going to use inverted index, which is a very simple data structure, but will help us avoid calculating that score for those documents. Okay, so this is the illustration of the inverted index. It consists of the dictionary and postings. The dictionary here is basically dictionary of our tokens that are pointing to their posting list. Sometime together with the token, you will have information about its document frequency, meaning in how many documents it appears. So here what you are seeing is a token in a vocab. In these curly brackets, you are seeing the document frequency of that token, which is how many documents that term appeared in. And this left side, our keys in our dictionary are pointing to posting lists. Posting list is the list of document IDs that contain this token. So here we have a document ID 3. That means document with the identifier 3 contains token how. And sometimes extra piece of information you will get is how many times that token appears in that document. As you can imagine how useful that's going to be if we are using this term frequency and inverse term frequency. So again, here at the bottom, we have more pieces of information. We have a token suite. It appears in 3 documents. So posting list contains 3 document identifiers, 1, 2, 3. Now, don't think it's 1, 2, 3 because here you will have 1 and 4, not 1 and 2. So don't think because there are 3, they need to come in a order of 1, 2, 3. And then next to each of the document ID, you will have the count of the term in this document. So what could I do? How can I use this? I have my query. I know which tokens compose my query. I can see all the document IDs associated with those tokens, and I can use only those documents to go out calculating the score between a query and each one of these documents, rank them, and then retrieve the most relevant ones. Okay, now maybe I should ask you this. I think based on the history of this course, this question will be somewhat trivial to you, but how can this approach be limited? Using BM25 to score, which is a fancier version of DFIDF to score documents given query. Yeah.
I think you already gave it away, but
Yes.
synonyms, just making an assumption.
Yeah. So we are working basically with statistics here. and we are bounded by the exact overlap of tokens in a query with tokens in the document, right? But so far in the course, we kept saying, oh, how that's insufficient for understanding the similarity of semantics of two pieces of text, because we have synonyms, relatedness, similarity, but not quite synonyms, and so on. So there's going to be an issue here, and specifically for the, for retrieval, it's going to require from the users to kind of build a mental model of what kind of words the author of a relevant document might have used, and then adjust their query based on this idea of what kind of words could be used in the relevant documents, which is, I think, experience we all had with using search engines. So as the solution was before, is going to be a solution again. Instead of using these, token overlaps, we are going to go into our vector space, right? So what we can do is we are super happy. We know there is birth, and we know we can concatenate our query with a document, right? And use that special separator token to separate them, right? So I don't know why it isn't shown here, but we would have CLS token, query tokens, separator token, and then a single documents tokens. And so we constructed the input. We make a forward pass through the encoder-based transformer like BERT that was pre-trained with mask language modeling. And at the end, like we have been using before, we can use the representation of the CLS token to represent the entire input, which consists both of a query and a document. By now, we know that all we need to achieve a single number is to make a product between that vector and appropriately shaped matrix, which will then give us a single score for that input. And that score can serve as a score of similarity between or the likelihood of these two, of the document being related to the input query if we are using softmax. There should be pretty, at this point, like you should be able to follow this, but let's stop here and see whether anything is unclear about this approach. You know all bits and pieces. Yeah.
Are you taking a cosine similarity to two CLS tokens?
No, we are not having at this point two CLS tokens. We have one because we have placed query and a document in the input. So there is just one CLS token that represents both a given query and a document. Of course, this if I had 10 documents, I would need to, for a given query, do this 10 times, right, to get the likelihood of that document being the relevant document for that query for each one of the 10. Okay. Is there any problem here? Not the problem in the sense this is flawed, rather some downstream problem you can see with this approach. And to kind of give you a hint, imagine you have a very realistic scenario of 100 million documents and infinite, constant stream of queries. Yeah.
We can take the document and query and pass it through the transform every single time, which might be expensive.
Yeah, that's right. So we are not, the answer was that we are not pre-computing anything. We need to compute every query document representation on fly. And the reason is these are both appearing in the input, right? So for a given query, if we had, 1,000 of them and then 100 million of these documents, you can imagine how many forward passes we need. That's a lot of forward passes, and remember, we need GPUs to actually make these forward passes in a reasonable time. Plus, we would need to store all those CLS vectors, and that's a lot of memory, unless we are really doing it as a streaming approach, and then we don't care about storing in memory. In any case, this becomes computationally intensive, right? So just to repeat, if a data store has millions of documents, then we can make millions of order passes and store millions of these vector representation for each query. So another way we can do this is a little bit more coarse in the representations we are creating, but it is alleviating some of these computational demands. And with this approach, we have separated the production of the representation of a query and production of representation of a document. There are two separate models. They can be the same, coming from the same model. So this can be an instance of a bird, and this can be an instance of the bird. We are recording their representation coming from CLS tokens. And now at the end, we have two CLS tokens, and we are making a dot product between them to say how similar the query is to document. What can we pre-compute with this approach? Yeah.
We can compute the CLS token for all documents.
Yeah, right. So now the document representation is no longer query specific as it was here, right? Here, query and document appeared in the input. Here, only document appears in this instance of, let's say, birth model. So that means if I had 100 millions of these documents in my data store, I can pre-compute their representation. And then for every query, I can call these representations to make these dot products. I don't need to compute them again and again and again. Is that distinction clear? I got a note from every side, but only one per side. Okay. The only issue here with this approach, and this approach is called dense passage retrieval or DPR, super used to this day, definitely should be one of your baselines together with BM25. The only issue with it, it's a little bit crude or coarse with these representations, right? In the end, you are having only a single representation of the entire passage, and you have only a single representation of the query, and you have only a single dot product to make a decision about their similarity. So this approach called Colbert, that's just a slight tweak to enrich the decision of whether a document is relevant for a query. It still uses two separate model instances to encode query and documents. You can still pre-compute all the representations of each document. However, at the end, instead of taking a dot product between two CLS tokens, it is taking every token's representation in a query, and it's looking for which token in the document piece of text is the most important for that token. And it's doing that for every query token. And then in the end, we just sum dot products between each query token's representation with its most relevant document token representation. So in a way, it's kind of more like contextual, you bring some contextualization here, right? As you are going through query tokens, you're looking at which piece of document text is the most relevant to that part of the query. And you combine all these pieces of information to, in the end, decide what is the similarity or a score, relevant score of a document to the query. Yeah.
But it's almost like just doing the first approach, but it's worse. It's like trying to mimic self-attention as being almost.
Yeah, right. Yes. So you can't have the full self-intention because then you need to have everything as part of the input, and you can't have these separate branches here. But then in the end, you are trying to bring some of that back. You are right. So it is worse than this approach, but better, conceptually better than this one. What is better or worse always depends on the empirical results, right? Okay, so this is another very commonly used approach that should be one of your baselines for the retrieval. Okay, now we are going to complicate things a little bit and talk about how to actually train retrieval model. So let's focus for the sake of simplicity on the DPR mod. I have taken BERT as my choice of a backbone model. I have made two instances of BERT, one that's going to encode queries, one that's going to encode documents. And now I want these instances of BERT to become specialized into giving me high scores when a document is truly relevant for a query. So it needs to produce a representation here at the CLS token at the end for a relevant document that together with this query documents representation will give a high score. And otherwise the score is going to be low. So we are now changing the weights of our BERT model to specialize for this particular task. Okay. We're going to go over stuff we are going to need, and then I'm going to write some details on the whiteboard. Okay. So the goal is to train a model to predict a relevance of a document to a given query by optimizing a similarity score or the dot product between their representation. The data we are going to need will require that I have both a relevant document for a given query and some documents that are irrelevant for a given query to be able to learn these good similarity scores. Positive examples will likely almost always come from data sets containing human annotated relevant documents. So you hire some people and you give them queries and you tell them, find me either on, let's say, if you're working on in a scientific domain, you'd say on archive, you need to find a document that's relevant, paper that's relevant to this query. Or if it's about web search, it would be about finding a relevant web page. But it's a quite intensive annotation task, and we can agree, right? Like someone actually does the search. And then for negative examples, we are going to use automatic approaches. So human, actual people won't annotate negative examples. So what people typically do, they sample the top 1,000 results retrieved by an existing retrieval. You kind of assume that it's not going to be perfect, and these 1,000 examples it's going to retrieve are going to be somewhat related, but not really related, and therefore they are great negative examples because they're not completely possibly relevant to the query. They have, something that can serve as a distractor, such that your retriever learns nuance differences between relevant and irrelevant documents. Okay, so instead of just sampling randomly, you take top 1,000 results from a baseline you expect to not work really well because you expect its top 1,000 results won't be as irrelevant as just a random sample of 1,000 documents. If we have no labeled positive examples, in this work, they have also proposed to use relevance-guided supervision. So we extract the top-ranked documents from an existing IR system that contained relevant answer strings, and we treat these as positive examples. And we use documents from the same top-ranked results that lack answer strings as negative examples. I kind of forget a little bit what is this about, but okay, sorry guys, I did forget a little bit about this relevance guided supervision, but in any case, you would do this iteratively. You would decide what the positive and negative examples are. You would train you would continue training your retriever, and then again repeat this sampling of positive and negative results and do this again. Okay, but let's this relevance guidance supervision it's maybe like a little bit advanced detail. What is important is this idea of having positive and negative examples. And now we are going to use the whiteboard to go over how to actually use those. Okay, so just as a reminder, we are trying to train dense retrieval models such as DPR. And we have just talked about what our data is going to look like. So we are going to have a query. We are going to have some positive passage. I'm going to use this notation here. Plus means that's a positive example. So positive example, which means a document that's truly relevant. Passage or document, it really, depends on from task to data set, what the, the length of the things we are retrieving is. These days, it's mostly going to be, I think, documents, but previously, because we were bounded more by the length of things, it was mostly passages. And assume this information comes from human annotators. So some annotator was tasked with given a query telling us for our training data purposes, what is the relevant document. And then we're going to have, for every query, we are going to have some number of negative examples. So here minus, because these are negative. And let's say we have, for every query, we have n of those. So I won't write this, but negative examples are documents that are not relevant to a given query. So I don't know if we had that question about when do we add hops to a brewing process, and now a negative document can be about, I don't know, in something irrelevant. Truly relevant would be like a Wikipedia page of a zebra, right? But as I just said, we don't want to have such negative results, because the difference between a positive and negative becomes so huge that the model can use some superficial cues. So it still has to be something seemingly related. Yeah.
So the idea here is that there's one singular positive example, but multiple negative examples.
We are going to learn about version where there is one positive, but it can be more than.
Okay.
Yeah. And in the data, very often it's going to be one, just because of the intensity of this data annotation process. Later, if you assume there is more than one, you can always use top 3 most similar documents, right? So even though later on you are retrieving more than one relevant, you can still learn your system with one relevant. Yeah. Okay, so the data is going to be, you're going to have a query, you're going to have its positive document, and we are going to have n negative documents. And we are going to have, let's say, d such. Okay, so our goal is to remember, we had those 2 instances of birth, right? And one is going to encode query, and the other one is going to encode document. And we have weights in one and the other. They are not shared weights, they are different weights. And here we are going to, I will call it E, I will call this bird EQ, and this one E, how do I call it? E passage, so EP. And I want, they are going to give me some vector representations. And when I make a dot product of those, I want to have a high score when these 2 are relevant, and I want to have lower score when these 2 are not relevant. So So some notion of similarity is going to come into a play, and we have seen various cases of training with positive and negative data. So far, remember we had word-to-vec was trained with positive and negative data. And even when we had our logistic regression, we had a similarity between our weights vector and our feature vector, determining the likelihood of our instance belonging to a certain class. So we always have this dot products and similarity being kind of correlated with the notion of importance. So what we are going to define is that the similarity between query and some passage is the dot product between the representation of that query with the representation of that passage. And this particular instance of representation we have mentioned so far that's still very used is to use encoder-based model that's pre-trained with mask language modeling objective. I keep mentioning BERT, but remember there are better versions of original BERT like modern BERT and the BERT version 3, right? So BERT for me, it's more like a placeholder for encoder-based family of models pre-trained with mask language modeling that uses CLS token at the beginning. So if we use BERT, that's going to then be BERT instance used for the query, for a query, and we are going to use CLS tokens representation at the end. And then for passage, we are going to do the same thing, but we are going to use the different instance of the BERT. Okay. Now, the goal becomes to learn weights of these BERT instances such that similarity of my query I, given its positive document that's truly relevant, should be larger than the similarity of query and these negative instances, which I have n. Sorry, this is probably, most of you don't see what I'm writing now. And now it's hidden here, but push it a little bit. Okay, so we want to learn weights of these two instances of BERT that's going to produce representations for a query and a passage, such that when I take their dot products, which is the similarity, it's going to be higher for between a query and a positive document than it is for query and its negative documents. So this is what we are going to do. We're going to place all these similarities for a given instance, for a given query, into a vector and apply a softmax. So I will have similarity of query I with its positive example. Then I'm going to put the similarity of query with the first negative example all the way to my last negative example. And I'm going to apply a softmax to this vector. And I'm going to pretend this is something like a classification problem where this is my true class. So this is now, once I apply softmax to it, I'm going to get a value from 0 and 1. And if this dot product is really high, this value is going to be very close to 1, as we know. And if this similarity was really low, the values are going to be close to 0, as we also know. And I'm just going to pretend that my true class is 0. So this is the probability of the true class. Although this is not a classification problem, but for the, we are choosing to frame it like this. Okay, so we have the first probability is going to be the probability of the true class, because this is where I placed my relevant document. And all of the other probabilities will be the probabilities of the classes that are not correct. So now, you know, in this course, we always use negative log likelihood training, right? So if I use my negative log likelihood loss, I know it's going to be the negative of logarithm of probability of true class, right? This is the most general version we have of the negative log likelihood training, right, in all cases. And here we know that this probability of a true class is this exact first value after softmax, right? So we have, just to kind of go over everything, we have constructed a vector where we have placed the similarities, which are these dot products, in an order like this. First one is the similarity of a query to its relevant document, that we know that's relevant because some human had said so, and then all negative documents and similarities of them to the query are placed next. If we think about this retrieval problem as I need to kind of predict the true class, where true class is the document that's truly relevant, then we know that the probability, the first one, is the probability of true class, because I place the similarity and the softmax value of it with the positive example in the first place here. So if I use negative log likelihood training, which will always be framed as minimize the negative log probability of the true class, then instead of probability of true class here, I can write the softmax value of this vector in the first position. So if I actually write that, maybe it's useful to remember what the softmax value is. Just to remind you, if I had the softmax, that's for trash. So softmax of some vector z1 to zk equals to, it's going to be a vector, right, from I to k. It's going to, again, have k values, and in each value, we are going to have e to the power of zi, and then normalize with respect to all other values. So this is a general equation for softmax. We have seen it about 1 million times now. So if I plug in, I mean, you should know what this equation is, but like if you don't mentally remember it for a second, like zoom into it and try to memorize it. 1, 2, 3, okay. Now, softmax of this thing in the first value is going to be e to similarity between query I, py plus, and then we are going to normalize with respect to all values in the original vector, but I'm just going to separate them between positive and negative ones. It's going to be n of e of the similarity between query and its negative example. Okay, so this becomes our loss, right? This is the loss that we use, which you can find here as well. So this is the loss. And just to repeat, we have our query. We have two BERT versions. We place query and document separately. Then we get token representation as CLS token from each one of them. We take their dot products to be this similarity. So now I have these similarities calculated, and I just need to plug them into this equation, and that becomes my loss. Then I use gradient descent, meaning I calculate gradients and update the weights here accordingly, right? And in this way, I have specialized these two BERT versions to give me representations in a way that those between a relevant document and a query will give me a high score, and otherwise I will get the lower score. And then I can later just use it for these purposes. Okay, I know this was a lot, but it's a great spot to stop. We are going to finish talking about retrieval next time, and then go into this answer extraction, answer generation, and so on to cover all of these architecture types. All right, see you on Wednesday.